All right, picking up where we left off at the last lecture, we had an answer here, and the two we're going to just kind of make a quick little comparison to is our answer under non-standard conditions and our answer because of standard conditions. So this is right on the back of the book, but we could have run some data here, do the same thing. We did it on a previous problem. And so if all of our pressures that we put into this equation were standard conditions, just one. Again, we had it listed up here that under standard conditions, 1 atm, 1 molarities, 25 degrees Celsius, and pure stuff, whatever. If we put all those into the equation, then where's our equation at? Here we go. Then this, of course, would end up just being 1, and then this would be 0. This whole thing would cancel out, and these guys would be equal to each other. That was not our case. And as far as this problem, taking a look at it now, we can sort of use Le Chatelier's principle and see how it would have pushed it as well. The product, ammonia, is 0.5, something less than 1. And here it is as a product. So if we do Le Chatelier and we pretend that we took some of this away, it should push becoming more spontaneous to products. And then again, if we look at what we did with hydrogen, ammonia was 1, so there's no effect on ammonia. If hydrogen is disturbed by adding more than 1, so 3, that is too much on a reactant side, which needs to re-equilibrate, and that's going to push also to products, which will become more spontaneous in the forward direction. So under both of these circumstances, it should make the reaction more spontaneous, and this gets to that weird wording we use here. It becomes more negative or less positive than what we have originally would have had, and we can see that reflected in the math. It's negative 44 as opposed to negative 33, so it's more negative or less positive, or as we said earlier, it's more spontaneous as a result of the changing conditions that we put it through. Okay, let's do another kind of scenario here. We're going to do a homework problem. So we'll slide this in. And we'll look at number 77. For number 77, the information says, explain qualitatively how delta G changes for each of the following reactions as the partial pressure of oxygen is increased. And again, we can approach this two different ways, and we will. We'll look at it with the equation, and we'll also just talk about it with Le Chatelier. So as far as an equation goes, we're going to use, how spontaneous or what change in spontaneity based upon this reaction. And if I'm not mistaken, College Board will not use this equation directly. What they will do is ask you to explain, and I think using a Chatelier explanation is perfectly suitable. But understanding the idea why it would drive one way or the other can be used mathematically here. So again, Q is the quotient of the volumes of stuff that we're given here. So we'll take a look at that. Q is the quotient. And if we just take a look at who we have here, oxygen, O2, is found in the denominator on the left-hand side. Of Q. And if the reactants or a reactant becomes larger, because that's what it's stating, it says if the oxygen is increased, if a reactant becomes larger, what does it do to Q? Well, Q becomes smaller. And delta G will also become smaller as a result of pushing the rest of the math through. And again, you could have answered this one also using Le Chatelier, saying, okay, if this is going to become bigger, disturb the system by adding more oxygen, that's going to drive the reaction more spontaneously to products. So I would expect a smaller Q value or a more negative, I said Q value, so I'm sorry, a smaller delta G value or a more negative delta G value. All right, same idea. Looking at oxygen in part B, oxygen's a product, so it's going to shift to the reactants as a result of that disturbance. And if we do that, it's going to become less spontaneous, and I would expect delta G to become larger or more positive. I'll just go ahead and write that down. Oxygen is in the numerator. And therefore, I get a larger Q, and as a result, a larger delta G. So it is more positive or less negative. Let's look at part C. Well, oxygen is also in the numerator, so it's going to do the same thing with maybe just a little bit more of an effect. And I'll write that out here. Is in the numerator. And it's raised to the third power. So it has an enhanced effect. Therefore, larger Q and also a larger, more positive delta G. And again, more positive being less spontaneous. It's in the forward direction. It's going to inhibit it moving in the forward direction. All right, back to the notes. Okay, so just a little bit more to go for chapter 19, but we'll probably have to make another lecture after this one. We won't get through the whole thing. We'll see how it goes. So based on the last equation, we're going to make a little change. If conditions return to equilibrium, the equation is going to change. And again, what we had previously, and we'll talk more about this again in just a moment after I get the whole thing down. So this is our equilibrium, or our equilibrium type equation, but it's some other weird conditions, whatever they happen to be thrown in there. Temperature in Kelvin, R value as far as in joules, 8.314. This is standard conditions, and this is just looking at spontaneity. What happened based on all those other circumstances we just talked about? Is it moving more spontaneously or less spontaneously from left to right? Okay, so we just said we're going to go to equilibrium. So if we're at equilibrium, I'm not moving from left to right or right to left. I'm there. I'm at equilibrium. So by definition, if you are at equilibrium, this value is 0. Delta G without the little naught thing is 0. And then just looking at everybody else here really quick, we'll just repeat stuff down. But we did say we were at equilibrium, so this is going to be K, not Q. And then if we just rearrange all this stuff around, we can rewrite it in this fashion. And this is one of the big equations that we can use. It's not what I call not a calculating equation. In other words, I wouldn't use this to calculate a K or a delta G. other than, this is the way I like to phrase this, it relates these two guys together. So if someone just throws some random values at you, the purpose is not to do a calculation. The purpose is, given K, what is delta G? Gibbs free energy based on these standard conditions. So let's take a look at a relationship just to get a kind of an idea of how these guys would go. Again, relationship between delta G at standard conditions and K. If, for example, I can do this either direction, and we'll just do it this way. If delta G here happened to be 0, and we go through the math, to make this true, what would K have to be to make delta G 0? Well, all of the K values, regardless, products of reactants, would all have to equal 1. Now, the odds and likelihood of that happening are almost like 0, but that's mathematically how they relate together. That one's just kind of make a base. Everything else will make sense. If we're looking at a positive value of delta G that is something large, something greater than 100, doesn't matter, something greater than 100, what does that tell you in regards to equilibrium as far as driving an equation for delta G? I'm sorry, for K. That would tell me that if this reaction is very, 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 very positive, does it move over to products? Do I have a lot of products? Think about K. K is products over reactants. Would you expect to have a lot of products if I have a very large positive delta G value? No. Relatively, the amount of products I have is going to be, and I'm just making these numbers up, it's going to be something really, really small. You're not going to have much product. And then the same idea, relating over to a really negative value, telling me it's very spontaneous in the forward direction, this reaction, I would expect to have a lot of products. And if I have a lot of products for K, I would think that this value should be something pretty large. Specifically, I don't know, but just give you an idea, some large K. And that looks like a pretty big number to me. So good enough for that. Okay, so we have this equation, and that's another good one we have. Now, if we had to reverse it around and say, okay, I don't want to solve this in regards to delta G, I want to solve this in regards to K. So we could go through and manipulate this around, and I'll do you a little favor. I'm not going to go through all the derivations for it. I'll just say K is equal to E raised up to a negative delta G over RT. And that's just deriving it from one equation to the other. So we could solve for either one of these variables based upon manipulating around one way or the other. Okay, well, that's the end of the notes. Let's go over to the homework problems and take a look at those. We'll start that off on a new lecture.